Okay, so for today's video, we're going to be talking about maximums, minimums, and Lagrange multipliers. So essentially situations of finding how to maximize your function in more than just one dimension. So in general, we're going to be talking about if you have a function with an arbitrary number of inputs, how are you going to find its maximum? All right, so let's go ahead and get started. So for the maximum minimums, there's a couple of requirements for something to be a maximum at a point A, B. First, your partial with respect to x at that point has to be 0. And hopefully you can guess that the second requirement is that the partial with respect to y also has to be 0. These are very similar to your conditions back in Calculus 1, so it shouldn't be that hard to remember them. Now, unfortunately, this does not guarantee the fact that you'll have a maximum or a minimum. Just like in Calc 1, it wasn't guaranteed that you'd have a maximum in. You have additional work that you have to do. So, here we had the second derivative test. We had one back in Calc 1. Well, all you had to do was take the second derivative and see if it was positive, negative, or 0. And that told you if it was a maximum, minimum, or point of inflection. Unfortunately, you don't have just one second derivative. You have 4 of them. So that's going to be a little bit more difficult. So you have to end up using this formula. So your second partial with respect to x times your second partial with respect to y minus your mixed partial squared. Now, this is of course assuming that you have two items so that the fxy and the fyx are the same thing, because this only really works for continuous functions. Now, what does this tell you? Well, you have 4 possible situations. If the total, so the d, is greater than 0, and f of xx is greater than 0, then it's a local minimum. So just like for your second derivative test, if it's greater than 0, that means it opens upwards, which means you have a minimum. If d is greater than 0 and fxx is less than 0, then you have a local maximum. Because again, back in Calc 1, if your second derivative was negative, then you had a maximum. Now, if d is less than 0, then it is not a local minimum or maximum. Guaranteed. This is usually going to be a situation of a saddle point. So it's the point where if you're looking one direction, it's a minimum. But if you look in the other direction, it's a maximum. So it's not either in the total situation. All right. Now, the other situation is d equals 0. Then you end up getting no information. That's kind of annoying if you end up getting that. But it does end up happening. Okay, so that's the basics for finding the maximum and minimums for a simple function in 3 and 1 dimensions. Now, sometimes you can have more than 3 dimensions, or you have some sort of constraint. And that is where Lagrange multipliers come in. This is a method where you figure out your maximum of your function given some sort of restriction. So back in Calc 1, you probably had a situation, well, I have this much fencing, what's the biggest area I can enclose? Stuff like that. But this is dealing with a lot more restrictions. So the total number of supplies you can have is a certain number. That's going to be your restriction. So to find the maximum and the minimum values of the function f of xyz, subject to the constraint g of xyz equals k. So your constraint could be anything, but it has to end up equaling some constant. Then there's a particular system you have to solve, and it's this one here. So the gradient of f of xyz has to equal to lambda of g of xyz, and you also have to solve the equation g of xyz equals k. So if you remember gradient, that's going to give you a vector of derivatives. So from this first half, you're going to be getting 3 equations, or equivalently, the number of equations based off the number of variables you have inputted. And then you have your second equation, which just gives you 1. So in this situation, we have 4 equations. And we also have 4 unknowns. We have x, y, z, and lambda. You have to solve for all 4 of them. So that can get a little ugly, but it's a basic system of equations. Now, this is why linear algebra is also required as a correct, because this is the case where it's actually very useful to have it. All right, so that's the system you have to solve. Now, what do you do with that? Well, you evaluate f of x, y, and z for all of the points that you found, and the largest one happens to be a maximum, the smallest one happens to be a minimum. That's straightforward. Now, there's a slight downside. There are restrictions to be able to use the Lagrange multiplier. First of all, your gradient of g cannot be 0. Because if your gradient is 0, well, that means lambda is 0, and it kind of messes everything up, and it's not that good of an equation. So you can't have the gradient equal 0 anywhere on your domain. It's just going to mess things up. The other thing is it's assuming that the extreme values actually exist. It's possible for an equation to not actually have any extreme values on it. And if that's the case, the Lagrange multiplier isn't actually going to help you at all. So if you're dealing with a function, you're going to want to have to take a look at some of the actual situations going on. All right? So hopefully that's informative for you guys, and I will see you in class.